ስለዚህ ዛሬ ምንድነው የምንማረው የቴርሞዳይናሚክ አፕሊኬሽን የሮኬት ቴርሞዳይናሚክ አፕሊኬሽን ነው። Because most of the phenomena that happen in the combustion chamber is related with thermodynamic phenomena. So because of that, we'll give emphasis for the fundamental elements of thermodynamics and aerothermodynamics. So under this section, what we are going to see is the performance of jet rocket, jet engine, rocket engine, nuclear or electric propulsion system. So that can be analyzed by 4 fundamental parameters. So these 4 fundamental parameters are the pressure, temperature, density and velocity inside the system. So that can be related with the combustion chamber phenomena. Okay. So we are going to see the most important phenomena like pressure, temperature, and density. Again, also the Mach number, in which our convergent divergent nozzle perform. So this can be the part of this discussion. So the 3 thermodynamic properties are there that are like enthalpy, entropy, and the internal energy. So in addition to pressure, temperature, and density, and the Mach or velocity instead, we can also use the enthalpy, the entropy, and the internal energy phenomena of the thermodynamics. So collectively, it is called thermodynamics and aerothermodynamics. So the analysis of propulsion problems can be made by the application of these fundamental thermodynamics and aerothermodynamics. So in this section, these fundamental thermodynamics and aerothermodynamics are particularly applicable for the propulsion can be seen. Okay, so sorry, it is problem of the mouse trigger now. Mouse stuck cargo now. Anyways, okay, so let's come to our discussion. Equation from the gas equation, we know the relation between the volume, the pressure, temperature, and the specific weight, okay, of the gas. So which is related with PV over WT. W means the weight, V is volume, P is pressure, T is temperature, which is equals to R, which is constant. So this R is the gas constant actually. So just presenting this thing with respect to specific volume, it becomes specific volume V is equals to the volume of an object divided by the weight. So when volume divided by weight, we can get PV over T is equals to R, so which is given as a constant. So this is just from ideal gas law. From the Charles and Boyle experiment, they observed this phenomena of the gas. Okay, so this is the gas law. So PV over T, which is equal to MR. So this MR is represented with another expression. So finally, the value of that MR is approximately 1,545.33 feet pound per pound mole R. So which can be expressed in the SI unit system, 8317 Newton meter per kilogram mole Kelvin. So that is the R value. So we can express the ideal gas equation like in equation number 5 here. So PV over T, which is equal to R over M, which is equal to R. So from that we can obtain pressure, density, temperature, and the gas constant are relations. So question number 6 represents how pressure is related with the density of an object, how pressure is related with the temperature, how it is related with the gas constant, ideal gas constant R. So actually we tried to see this phenomena at the very beginning in relation to the altitude. Okay, so these are varying quantities when we are climbing up and up. So we have already seen this thing, but it is just another continuation of that. Now let's see what the first law of thermodynamics states. So the first law of thermodynamics states that if a system undergoes a small thermodynamic change, that means a small perturbation of the change at near equilibrium condition, and if the quantity of heat energy entering the system through the wall is dq, while the volume is increased by dv by doing external work dw against the external pressure T. The change in internal energy dE is equals to dq minus pdv. So this is called the first law of thermodynamics. So we can see this thing by taking some specific volume, and so by doing that we can explain it later. So this is to say that the system exchanges its internal energy with its surrounding by taking in heat energy dq and doing external work dw, which is equal to pdv. Okay, so that is the meaning. So we have some terms which we have to define. Oh, actually, you are familiar with them in your thermodynamic course, but to make it clear for you in relation to the combustion chamber thermodynamics, we have to define some specific properties like specific heat. So if heat dq is added to the gas and the temperature rise dt is observed, then the rate of heat addition per degree temperature rise per unit mass of gas is known as specific heat. So we can present specific heat in two ways, in a constant volume process and in constant pressure process. So in constant volume process, it is formulated as Cp. Okay, Cp, which is equals to gamma R. In some books, you can find instead of gamma K. In many books, this gamma is represented with symbol K. So Kr over K minus 1, Cp means. And the specific heat at constant pressure process, constant volume process is Cv, which is R over gamma minus 1 or K minus 1 instead, you can use. So this is the two specific heat formulation, and this gamma or K in other case, which is Cp over Cv. It is the ratio of specific heat at constant pressure divided by specific heat at constant volume. It is not Cp over Cp, but it is Cp over Cv. Okay, you can make a small correction here. It is not Cp over Cv, but no, this is Cv, rather Cp. Yeah, so what is internal energy now? So the relationship between a specific heat at constant volume Cv and the internal energy E exists. So what is that relation? It is just from the first law of thermodynamics, you have dE minus the internal energy dE minus dQ minus pdV. That is first law of thermodynamics, that already stated here. Okay. So from that, since the internal energy is a function of its state, and therefore it is of any of two of gas parameters, PV, pressure is there, specific volume is there, temperature is there. So P, V, and T. any of these two combination. For example, this is the combination of temperature and the specific volume. Yeah, here also temperature and the specific volume combination. So internal energy, dE, which is equals to dE dV at constant temperature for the derivative of dV plus dE dt at constant volume. So here the volume at constant temperature, and here the temperature at a constant volume. So we can integrate this, and finally we can get the dE value. So this dE, change in energy, internal energy. Okay, so which is equal to dQ minus PdV. This quantity is equals to dQ minus PdV, because we have this relation which is relating internal energy dE. We have another equation number 11, another relation which relates internal energy. So by taking two equations, we have this equation number 12, which is dE dV at constant temperature plus dE dt at constant volume, which is equal to dQ minus PdV. So if heat is added under constant volume, then dV is equals to 0. That means the part which contains dV, PdV, and here also dE dV, these parts are 0. So what is left now? We have left dE dt, which is equal to dQ. That is the meaning. So we have left this component, so which is equals to CV, specific heat at constant volume. Okay, this quantity is equals to CV. In similar way, the internal energy for perfect gas from ideal gas law, we have D is equal to CV dt. Just taking this equation, any one of either this one or this one, we can relate it. So at constant volume, it is D is equal to CV dt. And we can integrate this one in order to find the internal energy E. So internal energy is equal to CV times temperature at particular moment plus energy naught. So E naught is the reference ground zero energy. Okay, this E naught is ground zero energy. So this is the relation for thermodynamic relation actually. Another specific heat and CP and CV, three things, CP and CV relation. So for this, the specific heat at constant pressure, CP, can be obtained by CV dt, which is equals to dQ minus PdV plus VdP minus VdP. Actually, this is just expanding this derivative of PV. Okay? So we can collect some terms and we can represent this as dQ is equal to CV dt plus dPV minus VdP. So this is the combination of the two. PdV plus VdP is given by the derivative of PV. Okay. So if the heat is added under constant pressure, dP is 0. So the component which contains dP is equals to 0. So that what? That means this part is 0. So dQ dt at constant pressure is equals to Cp, okay, which is equal to Cv plus, and that means from here you can rearrange and finally what you can get, Cv plus dPv dt. Okay, so this is the final relation. So which is equivalent for the perfect gas as this component is just R. Okay, PV over T is R. Therefore, we can introduce R here. So the gas constant R is equal to Cp minus Cv. So this is one of an important formula. That formula 18 is one of an important formula, like formula 14 also, again formula 10. So these are some of important formulas. And then the ratio, the specific ratio gamma, or instead K we can use, which is equal to Cp over Cv. And another Cp is equal to R times gamma over gamma minus 1. This is also another helpful formula. We have also relation of enthalpy with the pressure, the specific volume, and the internal energy E. Okay, so H is equal to PV plus E. This is the enthalpy formula simply. Okay, so where H represents the total heat content or total heat of the gas. So enthalpy means what? Total heat content or total heat of the gas. Okay, so this can be related with the previous formula. dq is equal to dE plus PdV. This PdV, this D of derivative of pressure and specific volume minus VdP will be similar to this thing. PdV alone, if we expand this one can be cancelled by another, so that we have left only PdV here. So which is equals to okay, this part, the dE plus dPdV is given as the enthalpy, the change in enthalpy. Okay, so we can substitute dQ is equals to dH. dH means dE plus d derivative of pressure and pressure and specific volume. So that gives us dH. Okay, so this is the formula for enthalpy. So therefore, if heat is added under constant pressure dQ, dQ is equal to dH only, because dP is 0 for constant pressure. The change in pressure becomes 0. So that we have left dQ over dt at constant pressure, which is equal to Cp, which is equal to dH over dt. Therefore, dH is equals to Cp dt. So this is also another important formula. Okay. Yeah. We can extend this discussion directly from the book. So let me stop sharing this one, and I will share another book that can illustrate more briefly than this my slide. So let's go to that part. So what we have discussed, the first law of thermodynamics. Okay, dE is equals to delta in Q minus delta in external work. So which is expressed in terms of this work done is potential energy and kinetic energy combination. Okay, dW. Okay, so in this manner we can express. Look, this is the best way to express the schematic way of thermodynamic system for the piston cylinder arrangement, but we can consider the B part. Okay, A part shows the piston cylinder arrangement, and there is system boundary here. Okay, on that. Similar to that, we have a system boundary, which is the combustion chamber. Okay, so the combustion chamber is considered system boundary, and the system will take place. Every thermodynamic process take place inside of this thing, and there is some external interaction at the exit. Okay, so this shows the rocket engine. So we already discussed this thing. It is relating even enthalpy. It is relating the internal energy, velocity. Okay, the height, the total energy. But let's go to the second law actually. What we have discussed before is completely the first law of thermodynamics, okay? That relates energy, heat, and external work. The second law of thermodynamics also there. So you are familiar with thermodynamics. I'm not going to teach you one-to-one, but once you know the basic things, okay, what are reversible process, what are enthalpies, what are entropy, then you can relate your knowledge to this process. So here, the second law of thermodynamics defines an important property like ds, dq, and temperature. So that is, ds is the enthalpy. Okay. No, entropy. Entropy means the disturbance of the system. When we introduce a small amount of change in heat, it immediately disorder the system under nearly in equilibrium. So entropy is just a system disturbance. Okay. Entropy, which expresses here second law in the express entropy. So that entropy ds is equal to dq over t. So ds is the change in entropy of the system under incremental reversible heat change. Okay, so dq is heat change. You know, temperature T is there. So the entropy being a state variable can be used either for reversible or irreversible process. You know what is a reversible process, and you know what is irreversible process. In irreversible process, the process will not iterate or can reverse, but it is only in the forward direction. But if it is reversible, then it can make a kind of loop. Okay, so if it is irreversible entropy, then we have ds, which is equal to dq over t plus d of s irreversible. So irreversible process have kind of some change. So that is what. So ds irreversible is generated due to irreversible dissipative phenomena. Means there are some heat loss, there are some dissipative conditions, then that irreversible process will undergo. So which is always greater than 1. Okay, greater than, no, not 1 by 0. It is greater than or equal to 0. It cannot be negative. Okay. So ds is also greater than or equal to dq over t for adiabatic process. Adiabatic process means what? Anyone can answer this? What is adiabatic process? Hello? Hello? Hello, hello? Yes, Amachu.
Addition of heat involvement. Yes, man.
So adiabatic process ማለት ነው
Addition of heat involvement process.
Heat?
There is no heat addition.
There is no heat addition or, yeah.
Doctor.
Actually, constant temperature condition. Yeah. Adiabatic process means constant temperature condition, or there is no heat addition on the process. So for such process, ds is greater than or equal to 0. Okay, so this is the meaning of this thing. So the heat per unit mass dq, which is expressed in terms of T times ds. So ds is the change in entropy per unit mass. So these quantities, the small quantities are all per unit mass. Okay, the capital representation indicates directly, for example, for Q it is heat. for S, it is just in entropy. But when we come to smaller letters, which represents per unit mass quantity, okay? So dq, delta q is equals to T times ds. So this is for the reversible process. And then which can be expressed as TdS, which is equal to du plus pdv. Now we are representing the enthalpy. Okay, this H indicates enthalpy, the enthalpy of the gas. So similar process what we have discussed at the very beginning, we are going to see those things. So dH is equals to du plus pdv plus vdp. So here, this is a specific volume. This is just pressure, okay? So from this expression, dH is equal to Cp dt. Just put Cp dt instead of dH here. By substituting that, we can finally get ds is equals to Cp dt over T minus RdP over P. So the main thing is what we are going to find is the pressure and temperature relation. We already derived this thing in terms of some other constant before, but now pressure at 2 divided by pressure at 1, which is equals to temperature at 2 over temperature at 1 times this thermodynamic constant, Cp over R. Look, Cp over R. That means pressure at 1 is, pressure at 2 means the combustion chamber pressure. You can see, you can give some point here, pressure at 1, pressure at 2, pressure at 3. We have 3 important regions in the combustion chamber. One of the region is this part, means the combustion chamber. We consider it as 0.1. We have another important region, truth region. That is the pressure, the temperature, and the velocity relation at 2. And this is 3, exit region. So we consider these 3 important regions for our calculation. So this thing gives you some brief idea about this kind of. So another is the isentropic process or reversible and adiabatic process. So for that, ds is equals to 0. The entropy is 0. Okay. So once the entropy is 0, we can find from the above equation Cp times dt over T minus RdP over P. So finally, that gives us P2 over P1 by integrating this thing, because we can find ln relation from here. From equation 211, ds is 0. And this is Cp ln of T minus R ln of the P. So that gives us P2 over P1. That integration is from 0.1 to 2. This 0.1, 0.2 are specific points which we consider for our calculation. So this is just thermodynamic process. So P2 over P1, which is equal to T2 over T1, the power of Cp over R. This is one of important formula in rocket science. Another Cp over R is equals to gamma over R, gamma minus 1, or K over K minus 1. This implies Cp is equals to R times gamma over gamma minus 1. Again, in terms of temperature, look, now in terms of only gamma, here we represented it in terms of Cp over R. So substitute Cp over R by gamma over R minus 1. So pressure 2 divided by pressure 1, which is equals to P2 by T1, the power of gamma by gamma minus 1. So this is one of our important formula. So understand these formulas, either this one or this one. And now let's define the pressure with density. Pressure 2 over pressure 1, which is equals to density 2 over density 1, the power of gamma, which means T2 over T1, the power of gamma. So that what is the relation between density and the temperature here? What is the relation between density? For example, density 2 over density 1 is equals to what? In terms of temperature, not pressure. Hello?
አቤት እየሰማን ነው ዶክተር።
እየተሰማችሁ ነው?
አዎ።
ስለዚህ what is the relation between pressure 2, no, density 2 over density 1 with respect to temperature? What is the relation? Just by looking this formula, 215. ምንድን ነው የሚመስላችሁ?
ዳይሬክት ሪሌሽንሺፕ ነው ያላቸው።
አሁን ለምሳሌ pressure density 2 over density 1 is the rest, the power of gamma, which is equals to temperature 2 over temperature 1, the power of gamma over gamma minus 1. ይሄን ፎርሙሌት ስታደርጉ ምንድን ነው የሚወጣው? density 2 over density 1 is equals to what?
T2 over T1, the power of y over gamma into gamma minus 1.
No. Check it again.
Over.
This is simply density 2 over density 1 is equals to temperature 2 over temperature 1, the power of 1 over gamma minus 1. 1 over. Okay. Arala? So this is what we call combustion chamber ውስጥ ያሉ ፕሮሰሶቹም በእንደዚህ በተለያዩ mass ወይም density variation, pressure variation, temperature variation, we can define in this manner. So these formulas are very vital for the combustion chamber phenomena. Okay, so these are some of important formulas. ሌሎቹ ወደ እንትን ስለሚሄድ thermodynamic calculations እና ኬሚካል ፎርሙላ ጋር ስለሚሄድ ይሄን በሌላ መልክ ምናየው ነው። የዚህ ፓርት አሁን የዛሬዋ ዲስከሽን ፓርት አይደለም። ኦኬ፣ ይሄ ማስ ፍራክሽን፣ የኦክሲዳይዘር ፍራክሽን፣ what we call this fuel fraction, what is the ratio of fuel to እነዚህን በሌላ ጊዜ የምናያቸው ናቸው። This is just chemistry, it is chemistry part. Okay, so እንደገና እንገባለን። አሁን ሰዓቱም አልቋል መሰለኝ። We have left only 2 minutes.